In this lecture, let us introduce the term FIR and IIR. Here, FIR means finite impulse response system. Okay, and IIR means infinite impulse response system. Okay, so this is a very simple concept. So finite impulse response and infinite impulse response refers to the length of the impulse response. Okay, it says the length of the impulse response. We know what we mean by impulse response, right? So this is my digital system. If the input is del of n and the corresponding output is called h of n, and if this length is finite, then you call finite impulse response system, and if the length of this h of n is infinite, then you call it IIR system. Okay, so if a system has h of n which is non-zero for capital N1 less than or equal to small n less than or equal to capital N2 and 0 everywhere else, that is our range of vision on the time axis is limited, that is finite, then you say it is a finite impulse response system. Therefore, your h of n is not equal to 0 over the vision. Let's say this point is capital N1 and this one is N2. Maybe I'll write down neatly. H of n is equal to okay, not is equal to 0. H of n is not equal to 0 for capital N1 less than or equal to small n less than or is equal to N2 and is equal to 0 elsewhere. Okay, such a system is called a FIR system. So in a FIR system, the output, if you write the convolution, it will be given by, see, we are talking about an LTI system. So y of n is equal to summation of x of k h of n minus k, where k is equal to n1 to n2. This is for finite impulse response system. So look at the limits. The limits are finite and there only n2 minus n1 plus one number of samples in the response. So y of n has n2 minus n1 plus 1 non-zero output. That's how you calculate the response of FIR system. On the other hand, if n1 goes to infinity or n2 goes to infinity or both n1 goes to infinity and n2 goes to infinity, then the system becomes IIR, infinite impulse response system. Okay, that means if the length of the impulse response is infinite, it is an IIR system. Now let us take an example. Let's take the moving average system, okay, which we already discussed in one of the lecture. Moving average system, right? So the moving average system is given by y of n is equal to 1 over capital M summation of x of n minus k, and the lower limit is k is equal to 0 and the upper limit is capital M minus 1. Right? Now look at the limit is finite, therefore this is an example of FIR system. Now what is h of n? What is the sequence of h of n? This we already calculated, right, in one of the previous lecture. So you have moving average system, right, and if the input is x of n, then the output will be y of n. This y of n is 1 over capital M summation of k is equal to 0 to capital M minus 1 x of n minus k. If you expand this, what will you get? You will get 1 over M, then x of n plus x of n minus 1, right, plus dot 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 plus x of n minus capital M plus 1. Now instead of applying x of n, you take the same moving average system, Now you apply the input del of n, and the corresponding output is called h of n. H of n is 1 over capital M summation of, instead of x you need to put a del of n minus k, and the lower limit is k is equal to 0 to capital M minus 1. So expand the summation 1 over M within a bracket, you will be having del of n plus del of n minus 1 plus del of n minus 2 plus dot 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 plus del of n minus capital M plus 1. This is my h of n. You take this m inside, you will be having 1 over m del of n plus 1 over m del of n minus 1 plus 1 over m times del of n minus 2 plus dot 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 plus 1 over m del of n minus capital M plus 1. How many terms are there? Capital M number of terms. This all are non-zero and these are equal to 1. Del of n is equal to 1 when n is equal to 0. Del of n minus 1 is equal to 1 when n is equal to 1. Del of n minus 2 is equal to 1 when n is equal to 2. Similarly, this guy is equal to 1 when n is equal to m minus 1. Therefore, I have m number of impulses. They are sitting at 0, 1, 2, 3 up to capital M minus 1. What is the strength of these impulses? 1 over capital M. All are scaled by 1 over M. So this is my impulse response. Okay, all samples are equal, and this type of output is called rectangular gate. It is in the form of rectangle, so it is called a rectangular gate function. Okay, therefore h of n is equal to 1 over m dot 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 1 over, and this is the 0th sample. Okay, so whether it is FIR or IIR, the output can always be written as a convolution. Okay, so whether you take it a IIR system or FIR system, the output of the system is always written as convolution of the input with the impulse response of the system. But the limit will depends on the nature of x of k and h of k. That's it. For example, this we already discussed, okay, if x of k is causal and so is h of k, that is the system is causal. If h of k is causal, this implies system is causal. Okay. Then x of k is causal means input is causal. If the input is causal and the system is causal, then the limit is k is equal to 0 to some finite value, let's say some n or something else, x of k and h of n minus k. This is my y of n. Now, how do you calculate this, or how do you compute this y of n? In the computation of y of n, whether it is FIR or IIR, we are only using the present values of the input. See, this is my present values of the input and past values of the input. We are not using any past values of the output here, and therefore this computation is non-recursive. Okay, we are not using the past output in this computation. Therefore, this shows that FIR filters can be computed non-recursively. Okay, can be computed non-recursively. And one more important point, IIR system or IIR filters can also be computed non-recursively. Okay, although in general IIR filters are more convenient, more convenient to compute recursively, it can also be computed non-recursively. In other words, okay, so not necessarily that IIR means you must go to recursive. Okay, so many textbooks make a mistake. Okay, FIR is not recursively, FIR is not necessarily non-recursive and IIR is not necessarily recursive. So very, very important point this is. FIR not necessarily non-recursive. Even FIR system you can use a recursive operation, and similarly IIR not necessarily recursive. Anyway you can use it. IIR you can go with recursive or non-recursive. Similarly FIR you can use recursive or non-recursive. Please clear this point. Okay. So recursive and non-recursive, these two terms are used to describe the process of computation. Okay, it has nothing to do with the length of the impulse response. Whether you recover feedback or you don't recover feedback, it's up to you. Recursive means we need the feedback. Non-recursive means we don't need the feedback. That's all. Okay, recursive computation requires feedback. Non-recursive does not require feedback. And as I told you, this convolution operation y of n is equal to x of k convolved with h of k does not make any distinction between FIR and IIR. This formula you can use it both IIR and FIR, it doesn't matter. Therefore, IIR filters can also be computed non-recursively, although in general it is more convenient to compute it recursively. Okay, so even though you are able to compute recursively, non-recursively for IIR, but it is more convenient I mean recursive computation is more convenient in IIR system. Okay, it is convenient, that's it. If you are interested, you can use non-recursive also for IIR computation. Okay, so similarly FIR filters can also be computed recursively. Okay, let us take an example for this, how we can write down the FIR filter recursively. So y of n is equal to x of n plus x of n minus 1. This is FIR filter, right? Well, obviously the computation is non-recursive. Is it recursive? No, it is non-recursive. Why? Because we don't want past output. No need of immediate past output. Okay, so in this expression doesn't have y of n minus 1, but we can write in terms of y of n minus 1. Okay, so I can also write as follows. Let me call this is equation number 1, and this one I can write as, replace n by n minus 1, y of n minus 1 is equal to x of n minus 1 plus x of n minus 2. Replace n by n minus 1 in equation 1. So let me call this is equation number 2. Now 1 minus 2 is equal to, this implies y of, in the left hand side y of n minus y of n minus 1, in the right hand side x of n plus x of n minus 1 minus x of n minus 1 minus x of n minus 2. This guy and that guy will get cancelled. So in the right hand side you have x of n minus x of n minus 2. Okay, and who prevents me from writing this as follows? Y of n is equal to y of n minus 1 plus x of n minus x of n minus 2. See, this is equation number 3. Now look at this equation 3. Is it a recursive equation? Is it a recursive computation? Yes, it is a recursive computation. Why? It's a recursive computation because I recover the present value of the input. Where is the present value? This one is the present value. Present value of the input. Okay, this one is the last but 2 input samples, and this one is last output value. Okay, immediate past output value. And this guy is last but 2 input samples. Therefore, my output depends on 3 components. One is present value of the input, last but 2 input samples, and past output values. Therefore, it is a computation with a feedback. See, you have y of n. This y of n depends on the previous output. So, there is a feedback. Therefore, this is the FIR system. So, FIR system can be computed recursively. Okay, this is the recursive computation. Yes, it is a recursive computation. Either you can compute using equation number 1 using non-recursively, or you can compute using recursively. It's up to you. Similarly, IIR can also be computed either recursively or non-recursively. The two terms should not be confused with each other. Okay, let us take an example of integrator. Okay, I mean digital integrator. So before we discuss digital integrator, let us discuss its counterpart, that is analog integrator. So what is an analog integrator? An analog integrator y of t is equal to integral of x of tau and d tau, and the limit is, lower limit is 0 and the upper limit is t. Okay, there should be some lower limit. Let's put this one is 0, and we assume that x of t is causal. Okay, the input is causal. Now if I wish to do it in the sampled domain, I mean in the digital domain, well, I can write this integral as follows. So sample it, sampled domain. Sampled domain means you are sampling it, right? T is equal to n times capital T. That's what your sampling process, sampled domain. Here analog signal and here sampled signal. So you take the sample at regular intervals, that is 0, 1, 2, 3 like that. Substitute n is equal to 1, 2, 3, 4 like that, and normalize capital T is 1. It can be 1 nanosecond or 1 microsecond or whatever it is. Therefore, let me call this is equation number 1. Equation number 1 becomes y of nt is, you have the signal like this, let's say 0, 1, 2, 3 and goes up to like that, and this point is t. Now what you do, this location is, let me call capital NT. What about this point? N minus 1 times t. Okay, so you integrate up to this point and denote that value as y of n minus 1 times capital T, like that. Maybe I will write down here. This is 0, 1, or you can put like this 0t, 2t, 3t, dot 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 dot, and this is n minus 1 times t, and this point is nt. So you are doing the integration from up to this point. This point to this point you are doing the integration 0 to nt. Okay, nt like this, and this one is n minus 1 times capital T. So my integration is 0 to t. In the sampled domain it becomes 0 to n times t, right? I'm sorry, like this. In the analog domain you are doing the integration from 0 to small t, x of tau d tau. Now once you do the sampling, then it becomes 0 to nt x of tau d tau. Now let me break this integration into different parts. So instead of integrating from 0 to nt, let me do the integration from 0 to n minus 1 times t x of tau d tau plus integral of n minus 1 times t to nt x of tau d tau, and this one I am going to denote by y of n minus 1 times capital T. Right, this is my y of t. And what about this? Okay, let me work on it properly because it is confusing. Same thing, but let me write it neatly. See, y of t is equal to integral of 0 to t x of tau d tau. The moment you sample it, you will get y of nt is equal to 0 to nt x of tau d tau. Now break this integral into two integrals, 0 to n minus 1 times capital T x of tau d tau plus integral of x of tau d tau n minus 1 times t to n times capital T. Now if the upper limit is nt, the argument is nt, output argument is nt. Now look at this integration. In this integration, the upper limit is n minus 1t. Therefore, this first integral I can write it as y of n minus 1 times capital T. And the second integral, let me write as it is, n minus 1 times t nt x of tau d tau. This is y of t. Sorry, in the transform domain nt. That's it. Okay, so I have integrated up to n minus 1 times t. Then I have integrated between these two intervals, n minus 1 times t to nt. Now I can approximate this second integration. How do I approximate that? The approximation is as follows. Because if you look at the time axis, between n minus 1th sample and the nth sample, there is no other value. It is 0. Okay, the samples are taken at the integer values. In between, the value is 0. You have non-zero only at the sampling instant. Okay, let's say this point is n minus 1 times t and this point is nt. In between n minus 1t and nt, there is no value. No values. Okay, I don't know the value in between n minus 1 times t and nt. In fact, it is not defined for a digital system. Therefore, let us approximate this. Okay, so let's take the average value between n minus 1t to n minus 1t and nt. So that average can be written as follows. You take x of n minus 1 times capital T plus x of nt and divided by 2. This is the average. After taking the average, you multiply by its length. What is the length? T. The length is nt minus n minus 1 times t. Therefore, this is t. That is why I am multiplying by t here. So, multiply the interval. So, the interval is capital T. This is the interval. So, this is how integration is carried out by a digital computer. So, this is called a digital integrator. Okay. So, the digital computer handles only digital numbers. So, this is called a numerical approximation procedure. Numerical approximation procedure. See, there are many algorithms for numerical integration. Okay, so this is one of them. Perhaps the simplest one is this one. Okay, this is the simplest one. The way we did in here is the simplest one. So you just take the average value of x of n minus 1 times t and x of n t and divided by 2, that is average. This is the average. Once you take average, then you multiply by the interval is capital T. Now if I translate this in the digital domain, what I will write is I will drop capital T here. Let us assume capital T is equal to 1 second or 1 unit, okay, or whatever it is. Not 1 second, let us say 1 unit, okay. Normalized to 1, it can be nanosecond or millisecond or whatever it is. I will drop capital T. So therefore y of n is equal to y of n minus 1 plus x of n plus x of n minus 1 divided by 2. Maybe see, I would like to drop the t inside the index, but I don't want to drop the t where we are multiplying. So I can write like this. So let's say this is equation number A. So from equation A, you can guess whether it is an FIR or IIR system. Okay, it is not obvious. Why? Only thing that I know that is being computed recursively. Okay, I can compute y of n recursively, but it doesn't mean that it is infinite impulse response system or finite impulse response system. Okay, I know that this is being computed recursively because I require y of n minus 1. Incidentally, this is what forms the basis of the so called bilinear transformation. This is called bilinear transformation. We will discuss in detail this bilinear transformation a little later, not now. Okay, but let's focus on this. Let's assume that the system is causal. If the system is causal, then what is going to happen? Causal means h of n is equal to 0 for n less than 0. Okay, if it is causal, then what is h of n? From this you can easily calculate h of n. Replace y of n by h of n, and this is h of n minus 1 plus t by 2, and here instead of x of n I put a del of n, instead of x of n minus 1 I put a del of n minus 1. For causal system, h of n is 0 for n less than 0. That means what? For negative values of index, the h of n is 0. So I start computing from n is equal to 0. Substitute n is equal to 0, then h of 0 is equal to h of minus 1 plus t by 2. Here del of 0 plus del of minus 1. What is del of minus 1? 0. This one is 1. H of minus 1, 0, because it is causal. Therefore, h of 0 is equal to del of 0 is 1, therefore t by 2. This is my h of 0. This will disappear, this will disappear. Keep computing like this. Substitute n is equal to 1, h of 1 is equal to h of 0, n minus 1, 1 minus 1 is 0, plus t by 2 del of 1 plus del of 0. And what is del of 1? Del of 1 is 0, and del of 0 is 1, and h of 0 we already know. Okay, from this is t by 2, del of 0 is 1, so it is t by 2, this is t. And substitute n is equal to 2. H of 2 is equal to h of 1 plus t by 2 times del of 2 plus del of 1. Now this is 0, this also 0. What is h of 1? H of 1 is t. Therefore, h of 2 is equal to t. Similarly, you keep computing this. For n is equal to 3, then h of 3 is equal to t. For n is equal to 4, h of 4 is equal to capital T. So, keep on goes, h of n is equal to t for all n greater than or equal to 1. H of 0 is different. So, it does not terminate anywhere. You can go to infinity. So, this list can keep on goes up to infinity. Therefore, the impulse response has an infinite number of non-zero values. Okay. Therefore, the impulse response is of infinite length. It is of infinite length. And the impulse response, if I draw it here, at 0 the height is t by 2, at 1 it is t, at 2 it is t, at 3 it is t, and keep on goes up to infinity like this. Okay. So, it would be t by 2 at n is equal to 0, it would be t at n is equal to 1, it would be t at n is equal to 2, it would be t at n is equal to 3, and so on and so forth. So, you can write this as h of n is equal to t by 2 del of n. How do you write this guy? Del of n minus 1. How do you write this guy? Del of n minus 2. T times del of n minus 1 plus t times del of n minus 2 plus dot dot dot. And this one, how do you write this one as? We need to write in in compact form. Okay. So, this you can do something so that more conveniently we can represent using standard digital signals. Okay. So, we know u of n, it has another half magnitude here, that magnitude we do not have. So, what to do in that case? So, in this expression you do one thing, you add t by 2 del of n plus t by 2 del of n minus t by 2 del of n, right, plus t times del of n minus 1 plus t times del of n minus 2 plus dot dot dot. Now, what about this? This is going to be t times del of n. Now, I can write this one plus t times del of n minus 1 plus t times del of n minus 2 plus so on so forth, then minus t by 2 times del of n. This guy I am writing over here. Now, if you draw this guy, this is t, this is t, this is t, del of n, this is del of n, right? What is the strength? 1, 2 and so on. Now, do not you see that this is equal to what? U of n, t times u of n. Therefore, this is t times u of n minus this guy, t by 2 times del of n. Simple manipulation, that is all. Therefore, your h of n is an infinite impulse response system, and recursion and non-recursion have nothing to do with the length of the impulse responses. Recursion, a very very important point in this one. Have nothing impulse responses. Okay. Any length of impulse responses can be computed recursively as well as non-recursively. As well as non-recursively. Okay, so that's all about the FIR and IAR systems, and in the next lecture we will enter into the frequency domain. Okay, so let me stop at this point. Thank you very much.